Each machine learning or statistical algorithm that you use for modeling has certain assumptions. It is important to understand these assumptions to trust the results of modeling. Any violation can lead to inaccurate and biased result. Assumptions of linear regression, linear relationship, independence of errors, homoscedasticity, normality of residuals, no perfect multicollinearity. Let's see our first assumption. Linear relationship between the variables. There must be a linear or near-linear relationship between the independent variable and the dependent variable. This can be verified by plotting the data points on a scatter plot. If the plotted points follow a straight line path, then we can say there is a linear relationship between the variables. The points don't need to be perfectly on a line, but they should generally show a trend in a straight direction. Even if path does not form a perfect straight line, we say there is a linear relationship between variables, and linear regression can be used. However, if the pattern appears curved or clearly deviates from a straight line, then linear regression may not be suitable, and we may need resort to nonlinear regression model. Independence of errors or no autocorrelation. This assumption is related to the residual, which is the difference between the actual data point and the regression line. Residuals are also known as noise or error. The error terms must be independent of each other. The error term of one data point should not influence the error term of another. One error term should not be correlated with another error term. If they are from different time period, they are likely dependent on one another. We have two ways to check this: graphically and using statistical test. To check graphically, we use scatter plot, where independent variable x is plotted on x side and residual on y-axis. When residuals are scattered randomly around zero, not revealing any pattern, then we can say that this assumption is met and error terms are independent of each other. If residual plot reveals a cyclic pattern or a clear trend like going upwards or downward, we can say that there is a violation of independence of error in linear regression and error terms are correlated. This is especially true if data is collected over time, or is a time series data. Although residual plots are an excellent way for visualizing autocorrelation, they can be subjective. One person may perceive as no pattern, while another might see a pattern, an evidence of autocorrelation. This problem may exist when pattern is not clear in the plot, so it becomes important to verify your visual conclusion by using statistical tests that give strong evidence of what you have visualized. The statistical test that is commonly used to check for independence of error assumption is Durbin-Watson test. This helps us to suggest how strong is the autocorrelation. Durbin-Watson statistics, D, ranges from 0 to 4. If the test result, D equals 2, then there is no autocorrelation. If D is less than 2 or greater than 2, then there exists autocorrelation. The rule of thumb is that values close to 2, between 1.5 and 2.5 suggest no autocorrelation. Values less than 1.5 and greater than 2.5 suggest autocorrelation. In the case of simple linear regression, we can plot independent variable x on x-axis and residual on y-axis. But what if we are using multiple linear regression where we have many independent variables? In that case, we can use predicted value of y on x-axis and residual on y-axis. Else, you have to visualize many residual plot for each independent variable x. Homoscedasticity, constant variance of errors. This assumption verifies how the errors are spread across the predicted values. This is the variance of errors. This is also verified by plotting predicted values y on x-axis and residuals on y-axis. It tells whether our model's residuals stay constant across the x-axis, or sometimes get larger or smaller in a pattern. If the spread of the error is constant throughout the range of predicted values, we say homoscedasticity is present. There should be no clear patterns like funnel-shaped or U-shaped. If residuals are randomly scattered, around 0, then we say that this assumption is likely met. Here, the residuals are scattered around the 0 line, but the points are not randomly scattered. Instead, they show a clear U-shaped pattern, and the spread is also not constant across the range of values on the x-axis. They are forming a clear pattern, so this is the case of heteroscedasticity. This residual plot shows wider spread on the right and a narrower on the left, indicates a funnel pattern, indicating heteroscedasticity. Here, residuals are smaller on the left F, and then becoming larger on the right. Wider spread on the left, narrower on the right. An inverted funnel pattern also indicates heteroscedasticity. To get the more confidence in what you have visualized, we can use a statistical test named Bruch-Pagan test. Bruch-Pagan test checks whether variance of the errors, residuals, in your regression model is constant. It is determined on the basis of p-value. Your statistical software will automatically calculate the required statistics. To know what is p-value, watch our video on p-value in the same playlist. The rule of thumb is that if p-value is less than 0.05, in our model residual variance deviates from the constant variance assumption and there is evidence of heteroscedasticity. If p-value is greater than 0.05, our model follows the assumption of constant variance and homoscedasticity is present. Normality of residuals. Errors must be normally distributed. You can check this using statistical tests like Shapiro-Wilk, Kolmogorov-Smirnov test or the Anderson-Darling test, and, graphically, using QQ-plot and histogram. This is histogram showing residuals forming bell-shaped curve. By looking at this plot, we can say that normality assumption is met. Now look at QQ-plot. Here, by plotting QQ-plot, we are trying to determine whether our residuals are following normal distribution. Blue dots closely follows 45-degree diagonal line, confirming that the normality assumption is satisfied. After inspecting visually, you can get more confidence in normality assumption by using statistical test like Shapiro-Wilk. Shapiro-Wilk test is good for assessing the normality assumption on small and medium sample sizes. The test statistics, W, ranges from 0 to 1. Value close to 1 indicates that the data closely matches a normal distribution. Value significantly less than 1 suggests that there is significant departure from normality. Before interpreting the result, it is important to know how significant the test result. To know this, p-value is calculated. Your statistical software like Python will automatically calculate test statistics, W and p-value for you. The rule of thumb is that if p-value is greater than 0.05, the residuals follows normality assumption. If p-value is less than 0.05, the residual deviates from normal distribution. The test result, W, suggests that the distribution of residuals is close to normal distribution as this value is close to 1. The p-value, greater than 0.05, suggests that our data is likely to meet the assumption of normality. No multicollinearity. This assumption is considered in multiple linear regression. Multicollinearity means that one independent variable has a strong influence on another independent variable. If this is the case, then we cannot determine how strongly one independence variable influences the dependent variable. If value of one independent variable can be calculated using another independent variable, then we say that multicollinearity exists. Multicollinearity will not be a problem if we are using regression analysis for prediction. But if we are using linear regression for making inference, to measure how one independent variable influences a dependent variable, we should check for multicollinearity. Thus, when we have to answer the questions like, why, how much, and what if, there should be no multicollinearity. The most popular way to detect multicollinearity is variance inflation factor, VIF. Each independent variable is regressed using all other independent variables using multiple linear regression equation. If this is the linear regression equation with 3 independent variables, then to check whether variable x1 can be predicted using x2 and x3, we have to apply above linear regression equation for x1, using this way. Similarly, the same regression have to be repeated for all other independent variables. Then VIF is calculated for each independent variable using formula. Now what is R²? To know what is R², watch our video in the same playlist. After you have calculated R² for each of these models, you can now calculate VIF for each of them. If VIF equals 1, then no multicollinearity is present for that variable. If VIF is greater than 1, then multicollinearity is present for that variable. Rule of thumb is that VIF between 1 to 5 indicates moderate multicollinearity, which is acceptable. VIF more than 5 indicates high multicollinearity, which needs attention. You need to assess whether this is problematic. VIF more than 10 indicates severe multicollinearity, which needs remedy.